In this video, I will go over an example problem of how we can use Imc method to design a controller for a first order process. And so the first thing we'll be given is the process, G tilde, the internal model. And G tilde in this case, because it's a first order, will be equal to Kp, the gain of your process, divided by tau p, the time constant of your process, times s plus 1. And so the first thing you do is find the Imc controller. And I abbreviate it Q. And what Q is equal to is this. We've got Q is equal to Q tilde times some filter I refer to as F. And Q tilde is equivalent to the given internal model minus, so subscript minus, and this refers to the stable part of the model. And by stable part, I mean no right-hand plane zeros, because we're working with an intrinsically stable process, and no lag. So in systems in which we've got very long pipes, for instance, we have to worry about dead time and time delays. That is where we would exclude it at this point. And so we would have G tilde minus times our filter F. And what this will be equivalent to is, to note here, G tilde minus is the inverse of the stable part of Q tilde. So we should have the inverse symbol here. And so what we'll get when we evaluate this is tau p s plus 1 over kp. And we will multiply this by our filter to make this referred to as a semi-proper system, lambda s plus 1. And this is to make sure that the degree of the numerator does not exceed that of the denominator. And so now that we know what our internal model controller is, we want to standardize it. So step 2 is to get GC and to get the feedback controller. And so to do that, there is an equation that we have derived previously via control block algebra, which tells us that it is equivalent to Q, the Imc controller, divided by 1 minus Q times the process model that we've been given. And so in that case, this is where the algebra starts to kick in and get a little heavy. We will have tau p s plus 1 divided by kp times lambda s plus 1. And we're going to divide this by 1 minus tau p s plus 1 over kp times lambda s plus 1. And we're going to multiply this by g tilde, which we have been given, which was kp over tau p s plus 1. And what we'll note here, which makes things nice, is we can cancel these terms out. The kp's cancel. The denominator begins to simplify. And after doing some more algebra, what we will ultimately arrive at is that our standardized controller transfer function GC is equal to tau p s plus 1 divided by kp times lambda times s. And this is equal to GC. And so now that we know GC, we're going to multiply it by tau p over tau p to get it into a form that more closely resembles a PID, and more specifically a PI controller in this example. And so when we do that, first we're going to recall the PI controller has a form Kc times tau is plus 1 over tau is this is equal to GC of a PI controller. And so we want to get this form to more closely resemble that. So by multiplying it by tau p over tau p, what we'll find is that tau p over kp times lambda times tau ps plus 1 divided by tau ps will be equal to GC. So these are these two forms are algebraically equivalent, and that is the main point here. And so what you'll note is how we can now see what KC is, as well as what the PI part of our controller should be. And so ultimately what we recognize is that tau I, the integral time constant in our controller, should be equivalent to our process time constant. And so the process time constant, just to give a little bit of background, is a physical law, or it's a physical law of your system. You don't have any control over it. We do pick what our integral time constant is, but the IMC model tells us to just let it be equal to what our process time constant is, and that's one less variable, one less tuning parameter that we have to worry about as a process control engineer, and that's why we like IMC based method. And in addition to that, we recognize what KC is equal to, and so that the gain of our controller will be equivalent to tau p over kp times this lambda. This lambda is a tuning parameter. And what the key, where the art comes in engineering, is figuring out how do you trade off between performance and robustness. We can only, so we optimize, or we want to favor one over the other in a given situation. That is a key tune. So we're going to tune for performance or robustness. And so you trade off between the two. You don't get all of either. So that is where a process engineer will come in, and they will test out different values of lambda to see which controller transfer function meets the needs of a given project. And so this wraps up how we can use the IMC design method to design a controller, a PI controller for a first order process. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.